I'm going to remember to hit record today. How's that? I forgot last time, so my bad. So welcome back, folks. So, Brittany, what did you ask me after class last time? I did it. You get a homework, and you get a homework. Said no one ever, right? 1, 2, 3, 4, 5, 6, 7. So yes, homework 6 is now available. Per popular request, and by popular I mean one person asked me, and so I said sure. It's a story that uses proportion correct as an outcome. So it's 10 points. Most of the questions are computational. It is shorter, a mere 58 questions. It is a random linear time model with 2 groups. So it's relatively straightforward in multi-modeling land. The only catch is logits versus probabilities. So this will be due a week from Friday, and let me know if you run into any problems or have questions. I fixed the errors in the key for the previous homework, so your scores and the pages should all be updated for that. So I don't suppose you have any questions yet? No? Okay, that's fair enough. All right. So we have then some more generalized models to work on. We were talking about ordinal data last time, right? Does that sound about right? So let's do a little reviewing then, because it is too legit to quit as the basis for everything. So you all know what a logit is. Everybody nailed that part of the quiz? Log of the odds of the probability of a 1. Yeah, of a 1 is the way I always set up the models, because we're always talking about something predicting more. Predicting the 0 doesn't make as much sense to me, but of course it's 6 to 1, half a dozen of the other. When I say unlogit, that's inverse link from logit back to probability. So Scott, you had said exponentiate before as a synonym. That's the intermediate one. So if you unlog it, you get to the odds part, and then you have to do one more step to get down to probability. So that's what gets you an odds ratio, is if you just exponentiate that. But all of these models that we're talking about for categorical data, meaning that they use a multinomial distribution, which is just a more than 2 category version of Bernoulli. It has as many p's as it has categories minus 1, because the last one has to sum to 1. So multinomial is the word that you may hear for this. But there are models for ordered categories, maybe ordered categories, or ordered adjacently, and then unordered. And they all work with logits or probits, the same type of things. The difference is how they divide the categories into submodels. So the one we're talking about looks like this. This is by far the most common way to treat ordinal data. It's called a cumulative logit. So it's C-logit in proxlimics as the link function. The cumulative part is because every submodel has every response in it. So it's not 0 versus 1 for the first submodel. It's 0 versus 1, 2, 3. So the way you can express that is the logit of greater than 0 as what the submodel is predicting. The second submodel is the logit of greater than 1. The third then is the logit of greater than 2. So whether your software predicts the red side or the green side is what you have to figure out in the first step. And I always try to set up my model so that it predicts the green side. So each of these submodels gets a different intercept for the expected logit of the red side or the green side when all of your predictors are 0. And you can figure out the predicted probability of anything in the middle by subtracting between submodels like this. This is called a graded response model in measurement model conveyance, in IRT models, by the way, same principle. And all of the software that I know of that treats this model assumes something called proportional odds, which means that every slope for predictors is the same across submodels. You cannot change the software for this assumption. It is built in. You have to figure out a way to estimate the model using some other proc or method in order to change this. And I'm going to show you how to do that today. So to say that in equation form here, if I have my 3 submodels for my 4 category variable, each of my submodels has a different intercept. So the prediction for whatever its y greater than starts off with a unique value, as well it should. But then from there, beta 1, beta 2, and beta 3 in this example are all the same. So it's predicting the logit of the higher category, whatever category that happens to be. So to me that is dissatisfying, but that is by far and away the most common way to set this up. And an alternative to this is a nominal model. That's the other one I'd say that is probably second most common. That one looks like this on the bottom with respect to the submodels. It treats your submodels as if you're dummy coding your outcome. So you designate one of your outcome categories as a reference, and the submodels estimate the probability of responding in each of the other categories relative to that one. So it's like, given that you answered 0 or 1, what's the logit that you said 1? Given that you answered 0 or 2, what's the logit that you said 2? And you can do math to get between these submodels. An easy way to set up a nominal model if you don't have software that will do it for mixed models is just to estimate the 3 separately. Because in the nominal model, the bottom one here, all the slopes are different across the submodels, and all of the random effects are too. So it really is like you're estimating 3 binary models at the same time. There's no saving in terms of number of parameters, so you may as well just separate your data and set it up the easy way. The other one here, this is partial credit. This is adjacent category logit. This one doesn't tend to be used as frequently for whatever reason. It just got started in M+. I'm not sure that it's in Glimix. This one is harder to find. So those are the ones that we're talking about here. So any questions on the setup? All right, so let's look at the example that we were doing last time then. So before I dive into that, when do you need an ordinal model versus an interval model? So this is the same distinction that you hear in the world of structural equation modeling or measurement modeling, like when can I just use a CFA versus when do I need to do something fancy involving logits instead? And I would say there's 2 things that you need to think about. Number 1 is distribution. So if you have, say, a 10-category outcome where most of the people are in the middle and there's fewer people on the edges and so the thing kind of looks normal, you can probably treat that as interval. If you have a 10-category outcome where most of the people are answering on, say, the low end and there's a lot fewer people as you go on, or vice versa, a linear model predicting that thing probably isn't going to work well because most of the information is in a tail and the prediction is going to want to go past the tail and not shut off like it needs to. So I would look at your distribution and think about not only how many categories you have, but how it's shaped and whether or not a linear prediction is going to be adequate. You can always run a regular mixed model and generate predicted outcomes and see for the levels of the predictors that you've actually observed, if it's predicting things like negative counts or negative values on an interval or an integer scale. If it's generating things that don't make sense, that's when I would go to something else. So it's not something that you can necessarily answer with statistics. There's not easy ways to do compare model fit between alternative distributions. There's something I mentioned in the slides here called a Wang Test. V-U-O-N-G is the author's name. He has some way of testing which distribution is more accurate than another. It's based on likelihoods, and to be honest, I don't really understand how it works given that each of the likelihoods would be calculated differently. I've seen people do this, but it's incorrect. You cannot use AIC and BIC to decide if you should have a normal model or an ordinal model. Those things are not calculated in the same way. Even though this is still maximum likelihood, the likelihood function that it's maximizing to try and find the height of is a multivariate multinomial. It's not a multivariate normal. So what height means is different. So saying something is taller in one model versus the other doesn't make sense if your units of tallness are not the same. So you can't do AIC and BIC. You can generate predictions and see if they look reasonable. You can do things like plot level 1 residuals and see if you're assuming they're normal, if they actually are. Otherwise, there's not necessarily hard and fast rules as to when you should switch over. But certainly, if you have some kind of variable that you have maybe only 3 or 4 categories, yeah, assuming integer and fitting a normal model is probably not going to be very effective. So this case for sure we have 0, 1, and 2, where most of the people are in the middle, but still categories. We need something that tells the model, hey, you can't predict things under 0 and you can't predict things over 2. So that's what the link functions here are going to serve to do. So we have here then an empty model, no predictors, single level. So this has a fixed intercept per submodel only. It is the worst model we can possibly have in the sense of prediction, but it's a baseline for getting our -2 log likelihood, as well as for making sure we know what the model is predicting. So in these ordinal models, how you refer to the different intercepts is you simply list them in the order in which SAS thinks they are there. Note that not the order that you would think they would be, but what SAS thinks they would be. So I had to figure this out the hard way. So in this first example here, SAS prints the logit for 2 instead of 0 or 1 first. So the first 0 in my estimate statement refers to that intercept. So even though it's the second threshold, it's the second split, second submodel, it shows up first. Job security, folks. But the good news is that you can always run these sorts of empty models and figure out what's what before you start adding anything that's going to make it more complicated. So I am asking for the intercept for the submodel predicting y greater than 0. So this is the logit of a 1 or a 2 instead of a 0. If I put a -1 there, it's predicting the red side instead. It's the logit of 0 instead of 1 or 2. Likewise, this would be predicting the green side in the PowerPoints here. Green side meaning this distinction, upper side versus lower side. This one right here is referring to the logit of an answer of 1 or 2 instead of 0. Hang on. Nope, 2 instead of 1, 0, or 1. And this is referring to 1 or 2, 0 or 1 instead of 2. Oh my goodness. Hang on. I need to reload here. Let's get this. See, I wrote it out so that I wouldn't have to figure this out in front of you. So this one is the logit of greater than 1, which means it's predicting 2. So if it's predicting 2, this one must be predicting 0 or 1. There we go. And if this one is predicting 1 or 2, this one must be predicting 0. And I-link gets you your probability that goes with it. There, we got it. So then down here, the logit of greater than 0, meaning that they have either some or full delirium in this story, translates into a probability of 0.63. That means the logit that they have a 0 instead translates into a probability of 0.37. So each of these submodels sums to 1, right? You're either predicting the 0 or the 1, 2, or you can be predicting the 1, 2 and not the 0. And in the other one, you're predicting the 0 or the 1, 2, or the 1, 2 and the 0. So it's using all of the data each time. If you wanted to know what the logit of just a 1 is, you would have to subtract between these two models. So I'm not going to lie to you, I find this thing hella confusing. I really hate this model. I hate it. And I hate it even more because after you go to the trouble to figure out these intercepts, everything else ignores these distinctions, that proportional odds thing, that you have a 1-unit difference in the logit regardless of what it is the logit of. That, to me, is logically inconsistent, and I don't like it. So now I'm adding a random intercept once I figure that out, the same as usual. Here's my Cove test. Do you remember this thing? This is a new piece of code, Cove test. it does a likelihood ratio test for you. And what 0 means is it's referring to the order of the terms in the G matrix, level 2 random effect variances and covariances. Right now, all we have is 1, so it's saying, hey, what would the model fit be if you gave it a 0 instead of a number? And it's giving me then the log likelihood difference between those two. So here's my random intercept variance. Two things to point out here. Do you remember what un11 means? That's actually the third thing, but we've talked about that one before. What does un mean? Unstructured. So it's saying, of the G matrix that's unstructured, what does 1, 1 refer to? Hey, this way for you guys. What am I doing besides voguing? Yes, I know the choreography from the video. Yes, matrix. Row 1, column 1. That's what I'm doing here. So un11 means that is my random intercept variance. It is the term in the unstructured G matrix at row 1, column 1. So this random intercept variance goes with both submodels. So even though each submodel is predicting a binary outcome, you can think of this as across a person's days, this is their tendency to have the higher value versus the lower value. You can think of it as almost like a proportion. So random intercept still means mean differences in this context, the same as it does for normal data. But in this case, the mean is the proportion of days in which you would have the higher value. So some people have a greater tendency to have more delirium. That shows up in a random intercept, the same as usual. And it shows up in the same random intercept regardless of whether we're talking about the tendency to have a 2 instead of a 0 or a 1, or the tendency to have a 1 or a 2 instead of a 0. What is normally under my random intercept variance? Residual, where'd it go? It's not estimated. And that's why in the equation for the ICC there, and this is what you will do in your homework, anytime you're working with logits, you get to throw in 3.29. That's the model scale ICC. This model scale versus data scale thing is something that is discussed in the new paper that I added. It is, where is it? This one. I cannot say either of these people's names, and it's a paper from ecology. I don't even remember how I stumbled across this, but it has some really helpful tables that describe how you compute the interclass correlation for different kinds of data, and how you would talk about it in the original scale of the DV versus the model scale, in logits versus probability. So you can look at that article as a reference to more about that, but this is model scale. So 3.29 is the residual variance because it's not estimated. In these data, once we know what the predicted probability is for each case, we know what the error or variance around it has to be. It's probability times 1 minus probability. So it shrinks the closer the probability gets to 0 or 1. So it's not that the model doesn't have a residual, it's not that it's perfect, it's that we don't need to figure out what it is. It's dictated by the mean. So it can't go down, you can't estimate it, it's never going to be here. So here are my two intercepts. I want to point out that they are different than before. So these probabilities are not the same as they were before the random intercept happened. That's because these are unit specific. They're interpreted as the fixed intercept specifically for somebody who has a random intercept U of 0. You can think of them still as central tendency, but mean is not technically accurate anymore. It's something more like median instead. Here's my Cove test. So this minus 2 log-like value that shows up here of 1035, that's what we should have had in the previous model if it was working correctly. Yes, that's what it is. Hooray. So it's essentially estimating a nested model for you, and then computing the difference between the two minus 2 log likelihoods. So that minus 2 log likelihood difference is the thing it's labeling as chi-square, and it's giving you a p-value to go with it. So I'm going to capitalize on its ability to do this in your homework. Normally when we add fixed and random effects, we do it one at a time, right? We add a fixed thing, we stare at the Wang Test p-value, we add its random part, we do a minus 2 log likelihood comparison. The reason that I do those in 2 steps is because most of the time we're in REML, which means that we can't compare minus 2 log likelihoods for models that differ in fixed effects anyway. So we have to keep the fixed part the same and then add the random. In maximum likelihood, you could, in theory, add both the fixed and the random slope at the same time, and your minus 2 log likelihood difference in ML would be using a degrees of freedom of 3. One for the fixed slope, one for the random slope variance, one for the covariance with the intercept. I don't like that, because if it's better, you don't know which of the things you added made it better. So I always do it in 2 steps. Now in this case, I'm going to ask you to go straight from an empty means random intercept model to the random linear time model, because as part of the output, it is going to implicitly estimate what the fixed linear time model would have been and do the minus 2 log likelihood comparison just against that. So you get both tests of both parts of the model separately within the same output using CoveTest, which is a good deal, right? Now, why haven't I made you do this the whole year? I'll show you in the next example. Sometimes it gets it wrong, and I don't know why. Or sometimes it can't figure it out. So I've seen that happen several times now, which is why I'm hesitant to try it. But in the data that I made for you that behaves perfectly, I ensured that it was going to work for each of you before I let you do it. So does that make sense? Do I need to say any of that again? It doesn't make sense, or you don't need to hear it again? I don't hear it again. We got it? Okay. Cool. So I don't know what this growth trajectory is going to look like across 13 days. I'm going to ask it to do a saturated means model with respect to day. So that's what this looks like. Day is being treated as categorical, so I'm asking for the mean on each day for each of the submodels. So this is going to be for the first submodel, and these ones down here are for the second submodel. And I used those LS means right here to make this picture in Excel. And I think this is where we left off, right? I told you I asked Excel to make me a trend line. Those are the black lines that were quadratic. That looks pretty damn linear, doesn't it? It looks bumpy, but it's linear. And the red line and the blue line look suspiciously similar, right? They have to. This is this idea of proportional odds, or basically parallel logits. Each of those coefficients for day is the same across the 2 submodels. And actually, in Stata, it doesn't even give you what the predicted logits are. It just gives you these offsets, because it really doesn't matter where you are on the y-axis. What you're looking at is this pattern here across the x-axis. So that looks linear. I went ahead and added a fixed linear slope. So I'm writing the model here in single level notation to try and highlight this idea of what's different between the 2 models and what's the same. So simultaneously, we are asking it to predict the logit of a score of some or full delirium, that's y greater than 0, and the logit of full rather than some or none, that's the logit greater than 1. So gamma 001 and gamma 002, the 1 and 2 are differentiating my 2 submodels. That's showing that each submodel starts off with a different intercept for what the predicted logit would be at day 0, which is going to be the first day in this case. And then here, I have a fixed linear effect of day, which does not have a third subscript. I'm trying to convey that this is the same fixed effect of day in both submodels. Likewise, my U0I does not have a third subscript. It is the same between models as well. So here's my fixed linear model. I'm asking it for some predictions for each of my two submodels to illustrate, again, the difference between logits and probabilities. And we'll notice here, too, stop by the random intercept variance. Day should have explained residual variance, but it can't. So that means random intercept variance has to go up. So the model has changed scale on us. And I think maybe I asked you guys to put this in a sentence to go home last time. Do you remember? So you might have the sentence written down in front of you, and you could read it and score participation points, which aren't a thing, but I'll remember you fondly. How's that? Participation points in my heart. What does my minus 0.07 mean? Woo! There it is. And you said the logit, which is like a third pronunciation, I would say, right? Well, logit, logit, or logit, right? I'll take any of those. Yes, I like it. Or log odds. So in the pretend write-ups, I have logit and then parentheses log odds, because there's certain people in the world that won't know what logit is, but they know what log odds are. So yes, the logit, however you pronounce it, decreases by decreases by 0.07. So it changes by minus 0.07 per day. So per day, we can't forget that part, because it's always per 1 unit change in x. And that looks like it's significant, right? Note the p-value is not the last column, that's gradient. And you didn't have to be any more specific than the logit of delirium, right? Because it's the same minus 0.07 in each of the submodels. So I've got the predicted intercept, and you're going to get to do lots of these in your homework. For day 0, the predicted intercept within this submodel for day 1, and the predicted intercept for day 2. And you'll note each of those numbers differs by the 0.07. So there is a linear change across days in terms of predicted logit. Likewise, here's my predicted logit of full delirium rather than none or some. It's not very likely, so it's a minus, it's a small number, because there's not a whole lot of people who had full delirium, but it gets more negative across the days, gets smaller. Now, what the hell is a logit again? We know what that is. But if you wanted to explain to somebody, what is a logit of minus 1.9? I'm used to seeing logits, and so I have somewhat of an intuitive sense of that. That's, you know, small. But negative means what, right? Do you remember that, Barch? The middle is 0. Less than 50, right? And it's further less than 50 the way further over you get. So here, this column that's called mean, what does the column give us? Proportion or probability, however you want to think about it. So yes, a logit of minus 1.9 corresponds to a probability of 0.1258. So that's what the model says. Your probability of having full delirium is by day 2. So if you look at the difference between these probabilities, they're not constant. This equal difference of 0.07 in logits translates into unequal differences in terms of probabilities. So that is the point that I'm trying to make with this last line right here. Nonsense, I-link. SAS will happily give it to you, even though it means nothing. It will convert minus 0.07 as a logit metric to a probability of 0.48. But nothing changes by 0.48 a day. It makes no sense. So you cannot ever unlogit a slope directly. You have to create predicted outcomes that are the result of the slope and unlogit those predicted outcomes instead. So order of operations, very important. Random slope, Same idea, asking if the logit of delirium changes differently across different people. And this thing right here, .00, is SAS code for, okay, leave in the first thing, which is the random intercept. We already know we need that. And pretend like the random intercept covariance with the random slope, which is the second thing, and the random slope variance are 0. So that's what this means. It's the order in which they will show up in the G matrix, which is always row, column the same, 1, 1, 2, 1, 2, 2, and so forth. And here's my test of that. Chi-square difference of 7, so -2 log likelihood difference is significant. Note what happens to my fixed slope here. It becomes non-significant. Does that mean I can kick it out? What do you think? Can I kick out my fixed slope because it became significant? Non-significant, excuse me. No? You're like, no? Right? No. SAS will let me, but I have a random slope around it. So random is always phrased as a deviation from the fixed. It's how far off your slope is from the fixed slope. So what this means is that on average now, it looks like this tendency to decrease across days is not different than 0, but people vary around that. So because people vary around that, because random slope variance is significant, we keep the slope that's in the middle, which is the fixed slope of right here. So now what we know is that people differ from each other in 2 ways. They differ in their susceptibility to delirium. So that's another way of saying mean differences, right? This is sort of phrasing it in more categorical language. They differ in their susceptibility to delirium at the beginning of their hospital stay, and they differ in the extent to which that susceptibility decreases. So let's figure out why. So do you remember what delirium means? I told you this like a week ago. Maybe? I was an cognitive aging person that day. What does it mean? You're nodding. No, yes, you, Kelsey. You can nod too, Scott.
When you take medication and it kind of induces delirium.
Yeah, it makes you look like you've lost your mind, like you either have Alzheimer's or some sort of like sudden cognitive impairment that is a complete side effect and is totally reversible. And it's more common in older people who have difficulty trying to figure out how much medicine they need because of their metabolism and weight and whatnot. So, one hypothesis, how would you tell if somebody has lost their mind? They would have to have been coherent enough for you to notice, right, that things have slid downhill. And so to the extent that people are more cognitively intact, you might be able to tell that they have slid downhill. So I'm using as this a predictor of something called the mini mental state exam, which is used to diagnose dementia. And the mean of that scale in this sample was 16 or thereabouts, and so that's what I centered it at. So I'm looking to see if susceptibility to delirium, or really the potential to be diagnosable, is related to cognitive status. That's my hypothesis here. So I'm throwing it in as both a main effect and as an interaction with day. So before I look at any results here, mini mental status was assessed on day 1. That makes it level 2 time invariant person something. So in this model, because it is a level 2 predictor, it can reduce my level 2 variance the same as usual. One's going to reduce one, and the other's going to reduce the other. We'll start with the one that's more obvious, maybe. The cross-level interaction of cognition by day is either going to reduce the day slope variance or the intercept. So cognition by day, is it going to reduce day slope variance? Show of hands. Intercept? Come on. At least vote, right? Cognition by day. The extent to which people show linear change depends on their cognitive status. That's my hypothesis in testing this cross-level interaction right here. Which of my two people variances is it going to reduce? Differences in change across days? That one. Yeah. Because it has day in it. Right? That's how you tell. So here's my two variance components represented as their ideas at the end of the line here. U0 is my random intercept, and U1 is my random linear day slope. So yes, part of the differences in linear change have to do with cognitive status. That's cognitive status by day as an interaction term. And part of the differences in susceptibility to delirium just at the beginning overall have to do with cognitive status overall. So a level 2 main effect predicts intercept variance. A level 2 interaction with a level 1 variable predicts the level 1 variable's random slope if it's in the model, which it is, or residual variance otherwise. So same principles as before. So let's see what happened. So I'm still getting this warning message from the log that something in the gradient is too big. And in this case, that's creeping into my fixed effects as well as my random effects. It looks like, if I look at the p-values that go with these two fixed effects here, the cross-level interaction of day by MMSE is not significant, whereas the main effect is significant. So if I interpret these coefficients in logits, let's do the main effect first. For every unit of cognitive status, the logit of delirium on day 0, right, specific, it's a simple main effect, goes down by 0.08, and that is significant. So in English, the more with it you are, the less likely you are to say they have delirium. And day by that, even though it's non-significant, we can still interpret it. Which pattern is this, folks? Here's my main effect of day that is negative. Here is my day by MMSE interaction, which is also negative. So what does MMSE do to my day slope? More negative, or stronger, bigger, right? Even though it becomes a smaller number on the number line, it's a bigger effect. It's a more negative slope. So the logit of delirium decreases more the more with it you are, non-significantly. And I included this data output for this particular model to highlight something for those of you who want to fit these models in Stata. Note my two intercepts. In SAS, I have coded these so that they are predicting the logit of the higher category. The ones that you get out of Stata are backwards. And this is what SAS tries to do for you by default, and it drives me insane. So your intercepts give you the logit of the lower category, whereas everything else in the model gives you the logit of the higher category instead. What the hell? I don't understand. But I couldn't figure out a way to switch it, so I let Stata do it that way. Here is, I also have that same model, by the way, in M+, for those of you who would want to try it in that software. It does the same thing. It gives you the logits of the lower categories, and then it gives you coefficients that predict the higher category instead. Hate. Okay. So let me show you now how to fix the proportional odds thing. There it is. Here we are. So these three fixed effects are all constrained to be the same across the two submodels. In Glimix, there is no way to fix that. In M+, to the best of my knowledge, there is no way to fix that. In Stata's MEO Logit, to the best of my knowledge, there is no way to fix that. The only way that I know how to fix that is to either flip to a nominal model where everything is separate, including the random effects, or to use a user-defined model, such as in Proc NL Mixed. So I've shown you Proc NL Mixed a couple of times. Anytime you find like a cool new model in a paper or a book, and you don't know how to fit it, but you want to try it, you can write it yourself in NL Mixed. So this is how to write a non-proportional odds ordinal model, where each fixed effect gets different between the two submodels. I've shown you this before, but it's a little bit tricky code, so we can go over it. I am asking it to do the same type of estimation that we're using in Glimix. Do you remember what Gauss means? Gaussian? Normal, yes. And qua-nu? Qua, it stands for quad. What's quad refer to? Quadrature or rectangling, broadly construed. So this is adaptive Gaussian quadrature with a Newton-Raphson something or another. That's what the new part means. With 15 points, 15 rectangles per dimension. Those are the same specifications that I used in Glimix to try and make sure that the results are otherwise comparable for that reason. In NL Mixed, it wants you to name every parameter that you're going to estimate and give it a starting value. I took the starting values out of previous models for the two intercepts. For all of the slopes, I just set the starting values to 0, and I made educated guesses on the variances. So B01 and B02, those are my intercepts per submodel. And then after that, my notation here is my first fixed effect, which is for day in submodel 1 versus 2. Then my second fixed effect, which is for the main effect of MMSE in submodel 1 versus 2. My third fixed effect for submodel 1 versus submodel 2, which is MMSE by day. So that's how I labeled these. You can label them however makes sense to you, because it's going to spit your labels back as part of the output. I then wrote out my linear predictor. Linear predictor means that it's your fixed and random effects together in one equation. So it looks just like the equation here, albeit in programming language. So here's my fixed intercept. Here's my linear slope for day. Here's my random slope for day, which I've named U1. Here's my fixed effect of MMSE on the intercept, the main effect. Here's my fixed effect of MMSE on the slope. So it's multiplying both predictor variables to create the interaction, and this is the name of the fixed effect. And then U0 is my random intercept. Skipping a few lines for a moment, the random effects down here, U0 and U1. So intercept, linear slope, each of those is supposed to have a mean of 0. That's what the thing in brackets means. And here is their G matrix, in order in which it will appear. V11, that's my random intercept variance. V21 is the covariance of the intercept and the slope, and V22 is the random slope variance. So they get starting values written up here. Now this part. Is anyone thinking, what the hell is that? And how did you know to put that there? Anyone? Because that's what I'd be thinking. Did I make this up? Nope. Someone else figured this out. It's right here. That's how the model predicts what the probability of each answer is. So I had to tell SAS to do the same thing. So here's the logit for the first submodel. Here's the logit for the first submodel. Here's the logit for the second submodel. And I put the spaces in so you could see the parallel structure. LL equals log means create a log likelihood instead of a likelihood, and it's the likelihood of P, which I've defined here. And this general thing means don't use any of your built-in stuff, use the thing that it said here. So if you ever find what looks like a cool new model that has the likelihood function, you can just write it in there. Walt Stroop's book, Generalized Linear Mixed Models, he has a bunch of examples in NLMix that you can steal online, and he has figured out the likelihoods, and you can just borrow that code and cite his book. So that's how you can do anything that's not built into software. You can figure out how to write the likelihood, you can estimate it in here. Last but not least, I'm writing estimate statements. These look a little bit different than the ones in mixed or Glimix. They look more like straight math rather than coefficients, but I'm just asking it to test the proportional odds assumptions. I'm asking it to estimate the difference in the fixed effects across the two submodels, because now I've let all three of them be different. And last but not least, I have a contrast, which is a multivariate Wald test for the three sets of differences as a whole. So that's going to give me essentially a -2 log likelihood-like comparison to see if all of this work is really necessary. Okay. Questions on that, or anybody want to hear again? Nope. Nope, you can just write it out in whatever's logical. General means that it is user-defined. So rather than saying, like, you could say something like, you know, normal or whatever, you can give it some sort of other distribution. General just means that it doesn't try to go look for it in its menu of options. It lets you write it out what it is here. Other questions? Yes. The contrast, yes. So it is 3 terms separated by commas, the same as in a regular contrast statement. It is the simultaneous test of whether there are any differences across the 3 comparisons. So it's like 3 sets of differences in the fixed effects across submodels. This is a multivariate Wald test for the fixed effects, for the differences between the fixed effects. Yep. So there are 2 ways using maximum likelihood that you can test multiple fixed effects at the same time. One is -2 log likelihood differences. That's what I did here. My new model is lower, taller, by 9.15. On 3 degrees of freedom, it fits better. So this extra effort that I put forth in estimating separate slopes for each submodel seems to be worth it somehow. What I get out of this contrast statement, F times numerator degrees of freedom is the same thing as chi-square. So it agrees to about the 2nd decimal place in terms of the differences in model fit. So here's what I get. I've divided this up by submodel here. So the first submodel is predicting the logit of 0 versus 1, 2. The second submodel is predicting the logit of 2 instead of 0, 1. And it looks like there is a slightly bigger effect of day in the second submodel, slightly bigger effect of MMSE in the first submodel, and maybe a little bit of difference in the interaction terms, but neither is significant. So this is something that I found confusing. The Wang test for my proportional odds came back as pretty close to significant. The -2 log likelihood came back as significant, but yet none of the 3 coefficients by themselves is different between submodels. So it's somewhat conflictory information as to what I should do next. What I did note, though, is that neither submodel looked like it had a significant p-value for the interaction of MMSE by day. And that was true in the model where it was combined across the 2 submodels. So I think that interaction term can go, and we'll redo it. So I dropped the interaction term from each submodel. Now I only have a linear slope for day and a main effect of MMSE. And here's what I end up with. So the first submodel has a non-significant fixed effective day, but a significantly negative main effect of cognition. And in the second submodel, they're both significantly negative. And it looks like the day slope is not different between submodels, but the MMSE slope is. So in English, cognition has a bigger effect on the logit of some or full delirium than the logit of full delirium. The end. And here's a picture. So I made these pictures in Excel. I gave you the spreadsheets with which to do so. Here it is. Let me open this up. So you can see how I made them. So I picked ±1 standard deviation to plot. A high score was 23, a low score was 9. That's somewhat arbitrary. I then wrote out an equation for a predicted outcome, which is fixed intercept plus the slope for day times what day it is, plus the slope for MMSE times MMSE. And in this case, the formula also holds a spot for the interaction term, even though I didn't include it in the model. So these are my predicted logits. And if you look at these pictures, logit is on the y-axis. The blue submodel is the logit of some or full delirium, whereas the red submodel is the logit of full delirium. Is that right? The legend is wrong. Let me get that fixed here. That is a copy-paste error, my friends. Yep. Here we go. Greater than 1. There we go. I'll fix the handout too. There we go. That's better. There. So full delirium is not very likely. That's why the red lines are lower. And it gets less likely as time goes on. So what do you notice about the shape of these red and blue lines here? Straight or bendy? Straight. That's because this is a linear slope of day in predicting logit. So it's a regular old model like we're used to when you predict logit. The difference between the solid and dashed lines refers to the main effect of MMSE. The fact that the blue lines are further apart than are the red lines is because MMSE has a bigger effect in predicting the logit of some or full than it does in predicting full. So this plot right here, I think, illustrates the interpretation of the coefficients as straightforwardly as possible. You can see that the linear slope of day is linear. The lines are all parallel. But look at the y-axis. Can you put that in a paper very easily? You could, but then you'd have to talk about what the hell a logit is. So to hedge your bets, you may want to convert those predicted logits into predicted probabilities, and that's what I did here. So each logit that I calculated from my model, I then back translated through an inverse link function And that function is e to the predicted logit over 1 plus e to the predicted logit. That gives me a predicted probability, which then looks like this. So this is where it can get tricky to explain to people what your model looks like. Because do these lines look straight or some of them look bendy? The bendy, though, is a consequence of probability being bounded. It's not that we threw in a quadratic or some other term that would make it bendy. It has to bend because it keeps going forever. So it's still a linear effective day, even though it doesn't look like it. And what happens to the difference between the lines? Like if you look at the red lines, they're further apart at day 0 than they are at day 12. When you look at non-parallel lines like that, your brain probably thinks interaction. But this model doesn't have an interaction of MMSE by day. It has a main effect of MMSE. But the consequences of that main effect of MMSE play out differently as you get closer and closer to the boundary of the outcome. So it looks like an interaction term. So this is the difficulty in trying to explain these models. Logit plots show the model as it really is. Linear slopes, constant differences as a function of the main effect. But what the hell's a logit? Probability plots are more intuitive for people who understand what probability means, but then the lines get all bendy and differentially squishy with each other. I don't know what the right answer is. Maybe both. And there's some M plus output. And there's some words. So you'll see in several places here, if I'm talking about a predicted value, I sometimes throw in or probability equal to this to sort of orient the reader as to what the hell we're trying to predict here. So this is how I would describe the results of this analysis. How's that? So your take-home message, proportional odds models divide an ordinal outcome into a series of submodels. Each submodel is binary and works with a logit. Other than letting each submodel have a different intercept, every other model parameter is the same across submodels. So then it looks a whole lot like a regular interval regression, multi-level regression in this case. But it may or may not be the case that each submodel should have the same parameters. You can test that. It's tricky, but you can test it. All right. Other questions? No? If you wanted to do a nominal model instead, remember what? No orders? Yep. Synonyms for nominal, generalized logit. It would be in SAS, for instance. You swap out one letter. Okay, watch carefully. C logit, G logit. Ta-da! What G logit does is assume no order. You have to designate which response category you want as the reference, and you get the logit of each other one relative to that reference. Every model parameter, including the random effects, is different between the submodels. So it really is like dividing your outcome into a series of binary outcomes and running them all separately, just that it's a simultaneous estimation. So C logit is cumulative logit, that's ordinal. G logit is generalized logit, that's nominal. Mult is the same because they're all assuming the same categorical probability distribution. other questions on that one? No? Okay. Can I show you proportions a little bit? We have a few minutes left. We can get into proportions. So proportion correct type outcomes, that's what your homework's going to be about. They work the same to some extent. These are outcomes that are bounded. They can't go below 0, they can't go above 1. So the logit link works well for that, handling the same type of creating boundaries in your predicted outcomes. The catch then is what kind of distribution your proportions take. So here's a picture. This is a binomial model. It is the same thing as Bernoulli, but just with more than one trial. So what it does is pretend like it's predicting the probability of getting any one trial to have a 1, and then it multiplies that by however many trials you have. So it works really well for percent correct type outcomes, which can be viewed as number correct out of number of possible trials. So in the middle here, this is what a binomial distribution would predict. The responses should look like if you had 20 trials and your probability of getting any one trial right was 50-50. Does that shape look familiar? Looks kind of normally, doesn't it? Yeah. So when do you need to worry about fitting a different type of model for proportion correct? Whenever your mean is off of 50-50. Normal models can approximate these outcomes fairly well at 50-50, even though it's discrete instead of continuous. But the closer you get to either end, the less well normal models work. So look at the green here. This would be if you have a ceiling effect. So if the mean for your sample, for instance, is 90% correct, this is what the binomial distribution says your outcome should look like. That looks pretty damn plausible, doesn't it? For an easy test, a really hard test would be the blue one. So it understands that it can't go past 100%. But it also expects that there's only one hump, and that observations should be reasonably well clumped around that mean. So binomial can't work for data that are bimodal, for instance. It predicts one hump. It also doesn't work as well without adjustments for data where there's sort of a tail here, right? Like if your test is easy for a lot of people, but then there's like some people out here that just don't get it, and they have some pretty low p-values. It doesn't expect that much variance, and the idea that there might be more variance than what it's expecting is called overdispersion. So I want to show you how to fit these models in Glimix because I think this is a pretty useful tool, and how to model overdispersion, which is something I just figured out this past year. So state of the art in terms of Lesa knowledge coming at you. So much so that if you download the same example that we were going to do from the last time I did this class, I totally screwed it up. I did not model overdispersion, and I'm pretty sure it's wrong. So I want you guys to know better. If you have data that the binomial doesn't work for, there's another one called beta. Do you see this crazy-ass shape here? This is from Wikipedia. Beta can take anything. Beta can predict bimodal data, the red line. It can predict skewed data in any which way. Beta is super flexible. The problem with beta is that it doesn't include zeros or ones, though. It goes between 0 and 1. So if you had people who got 100% or people who got 0%, you'd actually have to add 0 and 1 inflation factors on beta. And beta has parameters that are somewhat non-intuitive to figure out. So I'm not going to show you a beta, but I will show you a proportion one. So this example that I will start is based on a true story, as most of mine are. It was inspired by a true story, a publication that I helped with in grad school, which was published in 2004. And please don't tell me you were in grade school then, because I don't want to hear it. But this is a good example of how I knew just enough to be dangerous when I left grad school. I ran Proc Mixed. I had some more knowledgeable people helping me. We tried to do the best that we can, but we fit a longitudinal model to data that looked something like this. Now granted, data distributions are not necessarily indicative of a problem because it's always the residuals that we're modeling that have to have a distribution. But what do you think the odds are that that's going to have normal residuals, something that looks like that? Not so much. So old school approximations to deal with this problem would be to do arcsine transforms and to logit the DV and then run a regular model, right? So people do that. So I want to show you how one might go about doing a binomial model on this instead. So it's a subset of the data from the original paper, so don't take too much credit or too many conclusions with respect to the science of it, although the results are thank goodness, pretty much the same. But what we're looking at is growth curves across two types of kids, kids with speech-specific language impairment and kids with non-specific language impairment. So here is the syntax. There's a few twists to this. Link equals logit, you know that one. Dist equals binomial, you know that one. The new part, you give it a ratio as your DV of two variables. And you're like, what's that? Well, binomial is not actually for proportion correct outcomes. It's for number correct out of a certain number possible. So that's the format that SAS wants you to read it in and other programs as well. So I had a percent correct outcome that I translated into number correct, and then I computed a new variable that is the number possible. So in this case, because I already had percent correct, I decided that the number possible was 100. I created the number correct as the percent times the number possible, and I rounded it to the nearest trial. So if I only had percent correct, I have to do this sort of backwards transformation. But my guess is that you already had that information if you have percent correct. So the nice thing about this type of specification, by the way, is that there's a built-in factor if people don't cooperate. What if someone who's in your study lost their mind before they got to finish all the trials? Or they didn't get them all right, and so you threw out certain trials for some other reason, right? So there's a different n trials. You can build that in the model. So each person can have a different number possible as well as a different number correct. So here's my first model that has no random intercept, just to show you that what you get back is surprisingly intuitive. The fixed intercept in logits from this empty means single level model is 1.8. That translates into a probability of 0.86. That's the mean for these data. The mean percent correct is 0.86. That's exactly what the model predicts. But it does so understanding that that mean can't possibly go above 1 or below 0. So here's what I had screwed up in my previous example, was not paying attention to this number right here. If your distribution at level 1 is the right distribution, that number, Pearson chi-square over degrees of freedom, should be 1. 28 is not 1, as it turns out. So this indicates that there's way more variance than what this model predicts. The term for that is over-dispersion. And if you look at the picture, You see these tails down here? These are people that the model does not think should be down here. You compare that to the these predictions, it doesn't expect these tails to keep going. So there's more variance here than what the binomial model per se thinks there should be. That's called over-dispersion, and we have to build something into the model to be able to deal with it. Just adding in a random intercept, which is my next step, brings that number down to 13, but it's still nowhere near 1. So that's the new part of this example that I'm happy to show you. I figured out how to do over-dispersion and break that number down to something close to 1. However, in your homework, you don't have to do this. I built you binomial data that fit perfectly, so you don't have to worry about over-dispersion, because if I just figured this out 10 minutes ago, maybe I shouldn't make you do it for homework. That's my philosophy. Does that seem fair? Okay, so these models will run relatively quickly because I've built them for you to be able to do that. So come back on Wednesday for the exciting conclusion of binomial data and what to do when you have data that look like this. Any questions before we adjourn? All right, then office hours start now.